Welcome to CNCM's Computational Graph Theory lecture. This lecture we will be covering graph theoretical concepts that frequently occur and will be seen at the computational levels, but will not be seen at Olympiad levels or in other types of contests such as the United States Computational Olympiad. So first, we'll just be going over a few relevant terms, and the definitions aren't going to be precise. You would not pass a vocab test with these definitions, but they'll do for what we're teaching here. So a node is the fundamental building block of a graph. It has many names. It's called a vertex. There's other things, other ways you can call it, but edges connect nodes, and faces are a planar graph's regions. Most of these other terms, I won't read them out because you can read them, but of note, we'll see that we'll mostly be looking at undirected graphs, which are graphs such that the edges do not have a direction. And we'll be looking at the degrees of vertices. So check that definition. And at the very end, we'll check out some trees, which are just graphs with no cycles. Just to give you a brief idea of what a graph might look like, we might see this might be a node connecting not to another node. This will be A, this will be B. And so these would be the nodes, and this would be the edge. And there might be other nodes, and there might be other things going on. And so this would not be a tree that we've just talked about because it has a cycle, and the cycle would be this. And so we'll really be seeing that cycles are our primary focus when we're thinking about computational graph theory. But we also have Euler's formula, which is a very powerful formula. It relates the number of faces in a planar graph, the number of vertices in a planar graph, and the number of edges in a planar graph. And it says that in a connected planar graph with f faces, v vertices, and e edges, f plus v is equal to e plus 2. And this is a very important formula. And so our exercise is going to be, we assume this for graphs, and we want to show that it holds for polyhedra. And so this will be a proof-based exercise, and so we won't go over all the gory details. We'll just try to give you some motivation to this in case you're interested. You'll never be asked to prove anything on a computational contest, but we'll just take an example of a cube and a cube net. Yes. And we know if you fold the cube net, you get the cube. And this cube net will have vertices here. Vertices, which are also called nodes. And the cube, well, it's not a graph in the sense that we've discussed so far, but we can think of it as having nodes here, 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 and here. And the edges connecting the things, and the faces here would be f1, f2, f3, and here it would be the faces of the cube. And so Euler's formula says it holds for this, and we're just trying to show that we can show that if we assume it holds for this, that it holds for this. If you look at the number of vertices in both graphs, you'll see that they're not the same. If you look at the number of edges in both graphs, you'll see that they're not the same. And the number of faces is also not the same, which kind of implies that they're all kind of scaled up such that the same formula actually holds here, equals e plus 2. And just sort of interesting because the definitions are so vastly different, but the formulas kind of work out to be the same. Actually, in this graph, we actually consider this outer region as a region. So this would be f1, f2, f3, f4, and we might call this like f5. Let me delete this. Yeah, so the region that has no boundaries, that's also counted in Euler's formula. So we're going to go over a problem here. If a connected planar graph with v vertices, each of degree 4 has 10 faces, we find v. So I'm going to give you a second to try to work this problem out, and then we'll go over the solution. V vertices degree 4, 10 faces. I'm just going to check the problem again. Find V, right. Find V. And so the problem does give us that the graph is planar and connected, which are the prerequisites to using Euler's formula. And so since the previous slide was going over Euler's formula, you might think to apply that formula here. And so we'll just use the values that we've been given. And 10 will be equal to F, this will be 10. V is just equal to V, equals E plus 2. And if you check the definition of the word degree, and I believe I actually mentioned at the beginning, the degree of a vertex is the number of edges that are leaving it, I believe. So for example, this vertex A has degree 4, and so it might be a vertex you find here. And so if they all have degree 4, well, we have to use this information to find the number of edges in the graph. And so there's a very interesting lemma, which just says that the sum of the degrees of the vertices, di all I, is just 2 times the number of edges. And we can see this very easily in this graph. If you call this like edge 1, edge 2, edge 3, edge 4, then each edge both contributes to the degree of A and to the degree of the vertex that A is connected to. So each edge contributes twice to the degree sum. And so if we divide the degree sum by 2, we're going to get the number of edges. And so the number of edges would just be, well, there's 10, there's V vertices, I believe, yeah. And they each have degree 4. But then you have to divide by 2 because each edge is counted twice. And so you get plus 2 equals 10 plus V. And this is just a matter of algebra. You'll get 2V plus 2 equals 10 plus V. V equals 8, I believe. Let me just check my math here. I believe V actually equals 12. But the idea is not in the algebra. The idea is that you just apply Euler's formula and you'll arrive at the intended solution. Yeah. All right, now the second major topic we're going to be covering are cycles. So what are cycles? They're really just, if we go back to our notes slide here, cycles are just vertices that are connected to one another in interesting fashion. So if we have A, B, and C, we'll call this a cycle. This is a cycle of length 3, also denoted as C3. You can add D in here. This is still a cycle. You can add D, E, C. Now you have 2 cycles. You get the idea. As long as you're just going through different vertices and getting back to the same vertex, you have a cycle. If you have 5 vertices, for example, or 4 vertices, this is also a cycle. And similarly, if you have this, then now you have cycle 3, and you have a cycle 4, and you might have all sorts of cycles, right? So the reason cycles are so important is because most computational graph theory problems that are somewhat challenging utilize cycles as the main sort of theoretical concept. And so the main thing you really want to keep your eyes on is sort of places where you have to construct a graph and the problem statement tells you that there's going to be cycles. So here's just an example of a statement that occurs very often. If you have a function from a set to another set where both sets are discrete, then this is not an algebra problem. This is a computational graph theory problem. And what you really want to do in this case is just draw a bunch of vertices that are labeled 1, 2, 3, 4, and then you want to draw a directed arrow to signify that, you want to draw a directed arrow from X to Y to signify that f of X equals Y. And then if you want f cubed of x to be y, then all you need is a cycle of length 3, because then f cubed, you just go across the cycle. F of x is y, f of y is z, f of z is x, and so f cubed of x equals x. This is sort of the basic idea that you're going to be using in a lot of problems, and we'll take a dive into the deep end when we look at HMMT November 2015 problem 10. And so we see this thematic phrasing of the problem. The functions are from 1 through 101 to 1 through 101, such that f to the 101 of 1 is 2. And we're trying to find the remainder when n is divided by 103. So the first thing we want to note is that we're trying to find f to the 101, 1 equals 2. And so what that means is you don't actually have a cycle per se. You have 1, maybe something else, x, and then y. And then after like a 102 things happen, you're going to end up at 2. And the idea here is really that you don't want to deal with things that aren't cycles, because cycles are the main theory behind computational graph theory problems. And so you want to reduce this problem to a problem with cycles. And so that's our motivation for instead just considering f to the 101, 1 equals 1. And you might be thinking, well, this is not what the problem asked us for. Well, the thing is, if we find this value, we just sort of have to find how it ties into this value. And so we'll go on to the next slide. And I'll just paraphrase a few bits of the solution. We draw vertices and we number them. And we try to find the number of functions such that after the 101 of 1 is 1. We're going to walk through the how we find the number of functions. And it's pretty simple. So if f to the 101 of 1 is 1, then obviously we can have a cycle of length 101, right? We can have 1, 2, 3, all the way to 101, back to 1. And this clearly satisfies the constraints. But there's an interesting case. If 1 loops back to itself, and none of these things are connected to 1, then after the 101 of 1 is still 1. And so you might be wondering, so we're allowed a cycle of length 1, cycle length 1, cycle of length 101. What if there are other cycle lengths that work? And the key observation here is that the cycle length must divide 101. And why is this? Because if the cycle length does not divide 101, then if you take the elements in the cycle, and if it has like n elements, then if you take the 101th application of f, then you'll be taking the 101th element of this set mod n. And so this would have to equal the first element mod n. And so that means that n would have to be equal to 0 mod. No, that would mean 101 has to be equal to 0. 101 is converted to 0 mod n. And well, the 101 is actually prime. So these are the only two cases. Either 101 goes to itself, or either 1 goes to itself, or 1 is in a cycle of length 101. And note that when we drew our cycle that went from 1 to 2 all the way to 101, it doesn't actually have to go in that order. It can go 1 to 3 to 5 to 101 to 17. It just has to go through everything before coming back to 1. And so there's going to be 100 factorial such graphs when we have a cycle from 1 to itself of length 101. And we just think of this as ordering numbers 2 to 101 in some arbitrary order. And then we also have the case where 1 maps to itself. And in that case, we don't care about what any of the other things map to. So 2 through 101 can map through to anything. And so each of those numbers 2 through 101, which constitute 100 numbers, have 101 things that they can map to. And note that these functions do not have to be 1-to-1. So like 2 can map to 1, 3 can map to 1, 5 can map to 2, 7 can map to 2. It's just they just have to be functions. And so obviously we can't have something like this. We can't have one thing going to two places. And so this leaves us with 100 factorial plus 101 to the 100. We're going to write this down. N f to the 101 1 equals 100 factorial plus 101 to the 100, or there's 100 other numbers. So it would be 100 to the 101. And this is the number if f to the 101 equals 1 was the constraint. Now we're going to have to use the combinatorial properties of this problem to motivate us to use one more property of many computational combinatorics problems, which is symmetry. And so the symmetrical observation here is really that, well, we want n such that f to the 101 1 equals 2. So we might think this is useless. But the idea here is that if we find, let's call this n1, n2, and we can also consider the other n's. We can consider n3, f to the 101 1 equals 3, n4, f to the 101 1 equals 4, n101, f to the 101 1 equals 101. And what do these all have to add up to? All of these numbers, the sum of n1 plus n2, n101. Well, this is the number of graphs such that f to the 101 of 1 is 1, plus the number of graphs such that f to the 101 of 1 is 2, and then all the way. So this is just all graphs on 101 vertices. We've covered every single possible value that f to the 101 of 1 can be. It can be 1, it can be 2. All those things together, f to the 101 of 1 has to be something. And so if we cover all of these cases together, this is just the number of graphs on 101 vertices. And another observation we'll make is that n2 equals n3 equals n101. And why is this? Because there's no distinction between the vertex that we label 2 and the vertex that we label 3. Any graph such that there's like a cycle of length 101 that ends up at 2, there's a corresponding cycle such that it ends up at 3. We just switch the spots of 2 and 3, I believe. And so the idea here is that we know the sum. It's the number of graphs, and that's just, well, every number 1 through 101 has to map to something 1 through 101. And so for 1, there is 101 cases. For 2, there's 101 cases. To 101, there's 101 cases. And so there's 101 to the 101 total graphs. And now if we subtract minus n1, we'll get equals n2 plus n101. And what is n1 again? It's 101 to the 101 minus 100 to the 101 minus 100 factorial equals n2 plus n101. And we also said that n2 equals n3 all the way to n101. They're all the same. And so we'll say this is n2 plus n2 plus n2 because all those n's are the same, plus n101 equals this. I don't want to write that bit out again. And we're going to clear up some space here just so we can do the final calculations with a bit more ease. And so this is where we were just now. And how many terms are there here? It's just n2 100 times. So what this says is 101 to the 101 minus 100 to the 101 minus 100 factorial equals 102. And so we just divide by 100, we get 101 to the 101 minus 100 to the 101 minus 100 factorial over 100 equals n2. And we were trying to find n2 because ni was just the number of graphs such that f to the 101 1 equals I. And so this is our answer. We could do some simplification, and we'll actually have to do some simplification because, all right, so we can actually immediately simplify this to 101 to the 100 minus 99 factorial. Clearly 100 factorial over 100 is 99 factorial. And then I believe it was 101 to the 101 minus 100 to the 101 is just equal to 101 to the 100 times. Oh yeah. So we can do this as over 100 is just 101 to the 101 over 100 minus 100. Let me rewrite this a little bit just for ease of understanding. So the idea here is that 101 to the 101 minus 100 factorial over 100 is 101 to the 100. 101 to the 101 minus 100 factorial over, or 101, 100 to the 101 over 100 equals 100 to the 101. That's 101 to the 100. I'm sorry there. But this is just algebraic manipulation. And at this point, you're going to have to use some number theoretical concepts to figure this last bit out. But the idea is that you're trying to find this mod. I believe it was mod. Well, let's just look at the problem statement. It's mod 103. Mod 103. And so clearly this is just some Wilson's applications. 101 is just -2 to the 100, and 99 factorial is just 103 factorial over 102 times 101 times 103 times 100, and we'll replace this with a few more number theoretical arguments, and we'll leave out the last few computations because they're just not in the spirit of this lecture. But what we really get is that we'll get 103 factorial over, or we'll get 102 factorial over 102 times 101 times 100, and we'll replace numbers with their complements and their corresponding negatives. So we'll end up with 101 to the 100 minus 99 factorial is just -2 to the -2, which is 1/12, which is 43. And you'll actually notice that I believe if you just inverted the, what could you invert? There's a very interesting solution, because if you just take, if you just take 101, I believe 101 factorial mod 103 or something, you might get 12 immediately, and you're just multiplying 12 by 1, and that's what the entire problem boils down to, finding that the factor you're multiplying 12 by is actually 1. And so this is just to show that using this idea of cycles, you can tackle extremely difficult problems. We'll also talk about tournaments. These will show up a lot, but you will not have to really know much graph theory to understand them. The idea is that if you have a tournament where people play one another, A plays A and B, this would be an elimination tournament, not a round robin tournament. You can also model a round robin tournament. It's just useful to draw this as a tree, and that's why we like C and B. The people in the tournaments are modeled in this graph. That was not a very good graph. We'll have A, B, Maybe this is B again, this is C, maybe this is A playing against D. You get the idea. And it's just useful to envision this construct as a graph rather than whatever else you might want to envision it as. Lastly, we're going to talk about a few other topics in graph theory. So far, the main takeaways are that really computational graph theory can be viewed in a purely number theoretical way. And how you would do this is that if you want to think about like after the 101 of 1 equals 2, you would really just say, or after the 101 of 1 equals 1, the number theoretical way of saying this would be that the order with respect to f of 1 is 101 or divides 101. And this is very similar to orders in moduli when you're exponentiating things. You'll see that in those cases, numbers will also go to other numbers that are in the same set that they are. And numbers that divide the modulus will be in smaller cycles than numbers that do not divide the moduli. And so there's many parallels between number theory and graph theory. The last few ideas we want to talk about are trees. So these are two problems we can explore with trees. And trees actually do appear quite often in math. But we won't go over these problems because there's a few other topics that we also just need to briefly touch on. And the first of these will be adjacency matrices. Adjacency matrices are matrices that explain the connections between vertices in a graph in a purely mathematical way. So the advantage of using graphs over the number theoretical order idea is that you can kind of visualize what's going on. But when you're trying to write a program to do something, it's much easier to feed the program numbers than feed it an image. So how you'll do this is you'll sort of just have a matrix, and let's say B is connected to C, C is connected, or what I said. C is connected to A or whatever. Maybe C is also connected to D, right? So we'll just write a matrix, B, C, D. And we'll put a 1 whenever two elements are connected, and we'll put a 0 where two elements are not connected. This is how we feed the matrix, or this is how we feed a graph to a computer for analysis. So A is not connected to A, obviously, and none of these things are going to be connected to one another. But A is connected to B, to C, and not to D. B is connected to A. B is also connected to C, not to D. C is connected to everything, and D is only connected to C. So the idea is that this is a very usable format for computers because it's all numbers. You can think of this as an array of arrays, for example. And we said we wouldn't dive into more computer science sort of applications of graph theory, but a very important concept is that you might notice patterns in this is called an adjacency matrix, and these patterns are actually somewhat more suitable to training that you've been given outside of graph theory. Another useful use of adjacency matrices are that if you kind of square this matrix, you will get the number of ways to go back and forth between two vertices. And if you actually cube this matrix, you'll find, I believe, double the number of 3 cycles. And the idea is just that if you cube the number of, or if you cube this adjacency matrix, it'll find the number of paths of length 3 that start from A and go back to A. And so, for example, this cycle right here of length 3 would be counted once here. It'll be counted once as itself backwards, and it'll be counted 4 more times for each of the other vertices. So those are some uses of adjacency matrices. An issue with adjacency matrices is going to be that if you have a lot of vertices, you can't write that many vertices, and at that point, it kind of becomes only useful to people working with computers, which you will not frequently be doing when you're working in computational graph theory. The other idea is just a brief concept that on Eulerian trails, and the concept is that if you have a graph such that every vertex has even degree. Let me draw some more vertices, and you'll actually notice this vertex has odd degree. We'll have to sort this out. Let me just draw a simpler graph where every vertex has even degree. We'll draw a square, and we will draw another square. I don't think this is going to work. We'll just draw a square. And the idea is that, well, obviously all of these have degree 2. The idea is that if every vertex has even degree, then there exists a path, let's say starting on any vertex, such that you go over every edge in the graph exactly once and you return to the edge that you started at. And this is a necessary and sufficient condition. So this would be if for all v g dv 2 divides dv, there exists, and this is called an Eulerian trail. It's just a trail that traverses all the edges, not necessarily all the vertices. This trail does traverse all the vertices, but for example, there may be trails that do not traverse all the vertices, but do traverse all the edges. And traversing all the edges is sufficient for this. So this is if all vg 2 divides dv, there exists an Eulerian trail. And the proof for this is somewhat useful, but not for computational graph theory. If this ever shows up, it'll probably be apply this theorem once and then do something with the results that's not remotely related to graph theory. So if you're dealing with computer science, you'll probably need to know the constructive proof. If you're dealing with Olympiad graph theory, it'll be helpful to know the constructive proof. But that's all we'll leave here. And that's all I have for you guys today. So thank you for coming. Yeah, Eli, that's it.